Welcome back, everyone. I'm Gareth with Creative Connors. Today, let's chat about another component used in the trainee control circuit, limit switches. I want to show you a few different types that we commonly use in scenic automation, and then talk about how we wire them up for fail-safe operation. In my last video, I went over simple switch types and the terminology used to describe them. We'll put those concepts and terms to use today as we dissect limit switches and we see how to utilize them. If you're curious to learn more about how we developed the trainee schematic, I've recorded a separate deep dive video just about the schematic. Oh, and if you're not familiar with the trainee, it's a fun-sized stage model that you can assemble to learn about scenic automation. I'll put links to all this stuff below if you want to check it out. All right, let's dig in to limit switches. Limit switches are a simple sensor used to detect the position of scenery on stage. Most commonly, they have momentary actuators that are designed to be struck either by the scenery directly or by some part of the machine that is driving the scenery. On the trainee, you can see that the actuator is a small arm with a rounded tip that gets bumped by the wagon. Let's look at some other common actuators. The roller arm is a favorite. These can have either fixed length arms like this one or adjustable length arms. The roller at the end easily runs along the edge of whatever thing it strikes, so it doesn't get bound up. The rod actuator is super adaptable. These can be easily adjusted for shorter or longer reach. And the rod itself can be bent with pliers to craft just the right shape to reach the striking surface. The plunger style limit is actuated with very little travel. These can have a plain plunger or one with a roller. All of these come in a variety of sizes, from little petite micro switches up to big, chonky, beefy bodies. Some of them have heads that can swivel around, like this one. If I pop open the latch here, I can take the head and reposition it to a multitude of angles. This makes mounting really flexible, pretty handy. All right, let me grab a rotary limit switch to show that to you. This is a rotary limit switch. It can be mounted directly on a machine like a winch or a hoist. You can see it has a couple of micro switches and a stack of cams. The input shaft is geared to the cam stack so that as I rotate the input shaft, the cam stack rotates. The cams contact the micro switches. The full range of the switch is one rotation of the cam stack. You can spec the gear ratio between the input shaft and the cam stack. Say something like 15:1, meaning that it takes 15 revolutions of the input shaft to turn one revolution of the cam stack. Or 100:1, meaning it takes 100 revolutions of the input shaft to turn one revolution of the cams. The selected gear ratio gets you in the ballpark of the correct range of motion, and then you can adjust the exact angle of the cams with a screwdriver to really dial in the position of these limit switches. Let me run with this with a drill so you can see it work. Now, instead of a drill motor, imagine instead that this was connected to a hoist or a winch drum. Okay, there's more details we could cover on how to design a machine to utilize limit switches, or how to mount them and how to adjust them on stage, but that's really a whole other video. If you're interested in something like that, let me know in the comments below. Now I want to talk about the electrical contacts inside a limit switch. So let's take a look at a couple of examples. The switches on the trainee are single pole, double throw. On this switch, you can see that there are three terminals: the feed into the switch, a normally open contact, and then a normally closed contact. Looking at this wobble stick limit switch, it's double pole single throw. There are 4 terminals on the switch. One pair for each pole. The poles are different contact types. One is normally open and the other is normally closed. As I press the actuator, you can see the copper bars that span across the terminals moving. One moves to open the circuit and the other moves to close the circuit. Even though this one is double pole and this one is single pole, either one can be wired either as normally open or normally closed. So which way should we wire them up? Normally closed. Let's look at why. I've modified my trainee and I've added another limit switch midway across the track. I've wired up this limit switch as normally open. That will stop the motor when it hits the switch. It sends a signal back to the control circuit indicating that it's been hit. You can see the LED light on the relay has illuminated, showing you that the limit has been struck. This sounds pretty reasonable, right? So keep quiet until you're hit. Then let me know and I'll go ahead and stop the motor for you. But let's reset and see what happens if that wire connecting the limit switch to the rest of the control circuit were to come loose while it's moving. Okay, so I'm gonna start moving it again and I'll pull the wire off. Oh no! It crashes. Even though the limit switch was hit, it can't talk to the rest of the controls anymore because the wire was cut. And the controls, they have no idea that the wire was cut because the whole design assumes that everything is just fine until it hears from the limit switch. That's really optimistic. This method works okay as long as there isn't a failure in the wiring, but it falls apart as soon as anything goes wrong. We can't have that in a device that is meant to stop a motor. No. Instead, what we need is the system to be fail-safe. Now, fail-safe doesn't mean that it won't fail. Everything fails eventually, right? Rather, it means that when something inevitably does fail, that the system is put into a safe state. Now, in this case, a safe state would mean stop the motor if something were to come loose or go wrong or break or malfunction. Okay, let's try this again with the limit switch at the end of the track that's wired normally closed. This is the stock configuration for a trainee. Here the logic is basically, tell me all the time that you're okay, otherwise I'm going to stop. So if I start moving towards the limit switch, as soon as I disconnect that wire, the motor stops. That's much better. Now, if there's a failure, the motor immediately stops and it won't crash. The difference in logic here is subtle but important. Rather than designing it so it says, send a signal when to stop, it's send a signal as long as it is safe to move. If the signal is interrupted for any reason, either because you've actually hit the limit switch or because the connection to the limit switch has broken, the motor stops. It fails to a safe condition. Okay, so if we always wire limit switches normally closed, then why do they even have normally open contacts? Well, yeah, there are some times that we use them as normally open switches, specifically with interlock circuits, but that's a topic for another day. I hope this helped explain a bit about limit switches. If you'd like to dig even deeper, grab a copy of the Scenic Automation Handbook. I'll include a link below. Thanks so much for watching. See you next time.